Okay, so this week we're going to start off looking at section 3.3, which is on a couple different things. It's on the factor theorem. There's a remainder theorem, which is a nice way to, if you just want to know, like when you divide something, what the remainder is going to be. There's a quick way to find that without actually doing out all the division. You can just jump right to the remainder. And then we're also going to take a look at long division, okay, which, if you remember regular long division, it's not that much different. And it can be used all of the time, no matter what kind of division problem you have. There is a shortcut for long division called synthetic division, but it only works some of the time. So long division, what I'm going to show you today, will work all the time, but there is going to be a shortcut for some of the kinds of problems we look at, and we'll see that tomorrow. All right, so just a couple reminders about what a zero is or what a root is when we use these terms. So if I ask you to find a root to an equation, I'm asking you to find an x value that when you plug it in, you get 0. Okay, that's what it means to find a 0 or find a root. Right? And you can really say the statement both ways. It's a biconditional. You can say that if you have a root, then you plug it into a function and get 0. Or you can read it the other way. If you have a number that you plug in and get 0, then that number is a root. So it's an if-then statement that you can read either way. So what we're going to do is we're going to use long division to find roots of polynomials. Okay, and I'm going to show you an example first with just regular numbers. And then you'll kind of see we're going to do the same idea for polynomials. So let's say that I wanted you to factor the number 12. Okay, factor means to write it as a product of two numbers. And I know you could do that, but we'll just go through it. So I want you to factor the number 12, and I'm telling you that 3 is one of the factors. Well, what would you do with the 12 and the 3 to find the other factor? Yeah, you would divide. All right, so I already have it kind of written out. If you know 3 is a factor of 12, then what you're saying is 3 times something gives you 12. And as Allison just mentioned, if you want to figure out, well, what is the something? What is the other factor that you would multiply 3 by to get 12? Basically solve the equation up above for the something. Take the number you're trying to factor, divide by what you know is already a factor, and there you go. There's the other factor, 4. And the important thing is, when we divide by something that is a factor, there's no remainder. So if I asked you, is 5 a factor of 12? Well, you could try doing 12 divided by 5, but if you get a remainder that's not 0, it's not a factor. So that's kind of another important thing that always happens. When you take a number and divide by a factor, you get a remainder of 0. So that's how we can test if something is a factor. Pretty easy with just numbers, but now if I said something like x squared plus 3x plus 2, tell me if x plus 1 is a factor. Well, you could go through the same thing. Take x squared plus 3x plus 2, divide by x plus 1, and see if you get a remainder of 0. If you do, then x plus 1 is a factor. All right? Now that's one that you could probably factor in your head, so that's still not too bad. But we're going to do ones eventually you can't factor in your head. Right? And we'll have to test and see, is it a factor or not? So that's where a quick way to find the remainder is handy. Maybe we don't want to go through all the division. We just want to know if the remainder is 0 or not. And there's a way we can do that. Okay, so we'll get to that. All right, so that's what I just told you. If you take A and divide by B and get a remainder of 0, then you know B is a factor of A. So the reason we would want to factor not so much numbers, but we're going to focus on polynomials, is because it makes it easy to find the roots. If you look at something like, let's say, x squared plus 5x, actually let's go like this, x squared plus 7x plus 6. And I asked you, what are the two numbers you can plug in for x and get 0? Well, it's not super easy when you look at it that way, but if you think of it this way, x plus 1, x plus 6, now it's, oh, negative 1, negative 6. Okay, so factoring makes it easier to find the roots. That's why we do it. So we're going to use the same process I just showed you with the 12 divided by 3, but now we're going to do it with polynomials. So what I'll do is I'll do a problem at the same time we're writing the steps out. So there's 4 steps, so I would leave yourself enough room to write down 4 steps. Not super long steps, but you'll need a little bit of room. And does everyone have what's above the division algorithm for polynomials? Anyone still copying what's up above? Okay, so I'm going to go like this. And as I show you the steps, I'll do the step in the problem next to it. All right, so the first thing is, if the dividend, or the thing that's under the dividing symbol, okay, if that's missing a term, we need to fill in a 0 for that term, right? Because we want to keep things lined up in columns. So if we're missing a term, we need to fill it in. So if I look at what's under the root there, I'm missing the term that should have an exponent of what? Yep. I'm missing the squared term, okay, the exponent of 2. So I'm going to fill in 0x squared. So I'm going to put x minus 3, and I'm going to rewrite it just filling in the term I'm missing. So I got 1x cubed, 0x squared, minus 8x plus 3. Okay, so that's step 1. Fill in anything you're missing. Step 2, take the first term of the divisor, that's the thing on the outside, and divide it into the first term of the dividend, that's the thing on the inside. So the first term of the divisor in my problem is x. The first term of the dividend is x cubed. So we're going to divide x into x cubed. Right, so what do you get if you divide x cubed by x? Oh, Jacob? What do you get if you divide x cubed by x?
You get x squared.
Yep, you get x squared. Doesn't matter where you put it, you just put it up above. That's all you do in step 2. Divide x cubed by x, put the answer up above. Okay, step 3. Now you're going to multiply the answer that we just got. That's actually step 2. So take the answer from step 2 and multiply it to each term in the divisor. So it's kind of like you're distributing it back out. We're going to do x squared times x, and then x squared times negative 3. And this is where you have to line up the like terms. So make sure when you do that out, put the answer back under the column to make it like terms. Okay, so Tori, if I do x squared times x, what does that give me?
X cubed.
Yep, so x cubed. And now I'm going to do x squared times negative 3. So Kaya, if I do that, what's x squared times negative 3?
X squared minus 3x squared.
It's just going to be a single term. So it's just going to be a number in front with x squared right after it. Yeah, just negative 3x squared, and this is why we put the 0 in, because now I have a column for the x squared terms. So negative 3x squared. Okay, So that's step 3. Now, at this point in long division, what do you normally do next? So we did the divide part, the multiply part. What's the next step in long division usually? Yep.
Subtract.
We're going to subtract. So now we're going to subtract the columns that we just created, and that's in step 3. Now, you're not just subtracting one of them, you're subtracting both of them. So what I usually do is that. Okay, you're going to subtract both. So kind of think of that negative as being distributed to both. If you've done this right, the first one should always be 0. X cubed minus x cubed. That's gone. The next one is 0 x squared minus 3x squared. So Gabe, what's 0 minus negative 3x squared?
3x.
Yep, 3x squared. So now we did the subtraction part. And Chris, after we do that, what's the next step in long division?
You like bring the next part down.
Exactly. So the last thing is now bring down the next term, and you're going to do it again. Okay, we just keep going. Well, we don't keep going forever, right? So when do you stop? You stop when either you don't have any remainder, or the degree of your remainder is less than the degree of your divisor. There's the degree of my remainder. I just circled it in black. There's the degree of my divisor. I circled it right there. It's 1. Right now, the degree here is 2. The degree over here is 1. It's smaller. It started out as a degree 3, and it went down to a 2. But it's still bigger than what's on the outside. Okay, so I'm going to keep going. Okay, so bring down your next term. Minus 8x. Right, and now divide it again. So take the first term, which is x, and divide it into 3x squared. Right, so Natalie, if I divide x into 3x squared, what do I get?
3x.
Yep, positive or negative? Positive, yep. So divide it in. Multiply the 3x back out. So 3x times 3x is 3x squared. And Kathleen, what's 3x times negative 3? Yep, and again, just keeping it in that column. And Robin, what am I going to do with those columns now?
You're going to subtract them.
Yep, I subtract them.
So you would end up getting the 3x squared would disappear.
Yep, 3x squared minus 3x squared, that's gone.
And since it's a negative and a negative, you would add 9x to the negative 8x.
Yep.
So it would be positive x.
Positive x. So now I check, is the degree on my remainder less than my divisor? Not yet. Now they're the same. Degree 1, degree 1. So I gotta go one more time. Okay, so you keep going. And now this is going to be the last step. So we're either going to get a remainder here, or we're not. And then we're done. So bring down the 3. X divided by x gives me 1. If all they wanted was the quotient in this problem, you're done. That's the quotient. X squared plus 3x plus 1. If they want the remainder, I got to keep going. So 1 times x, 1 times negative 3. And some people get kind of excited. They look at it quick and you're like, oh, remainder 0. No, be careful because you're subtracting that. That part's 0. X minus x. But then 3 minus minus 3 gives me how much? 6. So the remainder is 6. So there's a couple ways we can write our answer. Well, one thing I can tell you is since we didn't get a remainder of 0, what does that mean about x minus 3? And what was under the division symbol? X minus 3 is what? It's not a factor. It doesn't divide into it nicely. If you were going to factor what's under here, you wouldn't use x minus 3. Okay. So we can write our answer this way. The quotient was x squared plus 3x plus 1. So you can write quotient and the remainder 6. You could write it separate. Or you could write it the way you would sometime if it was actual numbers. Let's say you had 12 divided by, let's do 7. If you were doing that with long division, you get 1 with a remainder of how much? 5. Okay. That's kind of how we just wrote it right there. Quotient, remainder. Or you can write it this way. Your quotient plus your remainder over the denominator. 1 plus 5/7, or 1 5/7. Oh, I can do exactly the same thing here. I can take my quotient, x squared plus 3x plus 1, plus my remainder, which in this case is 6, over my original denominator. So if we go back up, the original thing that we were dividing into it was x minus 3. And what I can do, I'm not going to do this for all problems, but I can graph what we just wrote as the answer. X squared plus 3x plus 1 plus 6 divided by x minus 3. Okay, so that's what we wrote. And now I'm going to write the original problem, okay, before we did all the work, and see if we get the same graph. If I get the same graph, then that means I probably did it right. So I'm going to take the original problem, which was x cubed minus 8x plus 3, and I'm going to divide by x minus 3. If I want, I don't even really have to look at the whole graph. I can just look at, oops, let's see, did I type something wrong? X cubed minus 8x plus 3, x minus 3. Oh, I should, well, that should be okay. X squared plus 3x plus 1 plus my remainder over my, oh, I probably need parentheses around this. Let's see, if that doesn't work, then I'm in trouble. All right, now it works. So I'm just checking to see, I should get the same answer either way, if I type in the problem we did or the answer we got. So I'm just trying some different values. Looks like they're coming out the same. So if I hit graph and they look exactly the same, then that probably means I did it right. So that was the answer we got, and that was the original problem before we did any work. Exact same picture. Okay. So which way they would like the answer, either top or bottom, you just have to read the problem and see what they say. Okay. But these are both correct. Yeah?
In the beginning of the problem, when you put the 0 in front of the x squared, do you only have to do that in front of the x squared if there's no?
You only have to do it in front of the ones that are missing.
Okay, so
Yep.
you wouldn't have to do it in front of the x to the third?
Nope, because the x to the third term was already there.
Okay.
So you have to look at the highest exponent, and then every single term from the highest one to the lowest one has to be there. So it would be really lousy if you had something like x minus 2 divided into x to the 12th plus 6. Because now you have to fill in zeros for x to the 11th, x to the 10th, 9th, 8th, 7th, 6, 5, 4, 3, 2, and 1.
Okay.
You have to fill in zeros for every single one of those. Unless you use synthetic division, which is a lot faster. And you could use synthetic division on that problem. Yeah.
I'm confused on how you got the x squared.
The x squared?
Yeah.
So that was when we did x cubed divided by x. That's how we got the x squared. And we're gonna do another one too. So we'll look at another one. Let's look at this one. So this time I've got 2x squared plus x plus 1 divided into 2 2x to the fourth minus x cubed plus 0x squared plus 0x minus 2. So it looks like on this one, they've already filled in the terms that were missing. The squared term was missing, and the linear term was missing. And if you're like, well, why do we even write them then? If they're 0, they don't really matter, right? Right, they don't really matter. But when we go through the problem, we have to keep things lined up in like terms. So what I've done is I've created a spot for everything that I could get. Cubes, squared, linear, constants. So we can keep everything lined up. Okay, so we're going to take that term and divide it into that term. That's our first step. So what's 2x to the fourth divided by 2x squared? Yeah.
X squared.
Yep, x squared. And you know you did it right as long as you know how to multiply monomials. If you multiply it back out and you get what you started with. So x squared times 2x squared gives me 2x to the fourth. X squared times x. Okay, so we're here, here, and here. X squared times x is x cubed. Put it under the x cubed. X squared times 1 is x squared. Put it under the x squared. Okay, and Nathan, what am I doing with all those columns now?
What do you mean?
Like, what's our next step?
Oh, you'd want to subtract the...
Subtract. So make sure you put it in parentheses and subtract everything. 2x to the fourth minus 2x to the fourth, gone. Would have been nice if the x cubed canceled out here, but it's not going to. So Gabe, if I subtract negative x cubed minus x cubed, what do I get? Think of it as like negative 1 minus 1. Negative 2, except this is negative 2.
X squared.
Remember, when you're adding and subtracting monomials, exponents don't change. So you're just going to have more or less x cubes when you're done. But you can't change the exponent. Anyone help them out? Yeah?
Negative 2x cubed.
Right, negative 2x cubed. Okay, so I'm not really going over rules for multiplying and dividing and adding monomials. If you have questions on it, come see me. Might find it in your book, but probably not because it's more of like an algebra 1 thing. Okay. All right. So negative x cubed minus x cubed is minus 2x cubed, and then 0x squared minus x squared, which is negative x squared. And now each step, your exponent should go down 1. Or sometimes it goes down more than 1 if you get a couple things that cancel, but we haven't had that happen yet. So we had a 4, now we have a 3. We have to keep going till it's smaller than a 2. Okay. So let's look at the next thing. Negative x cubed. Okay, so we're going to divide 2x squared into negative x, 2x squared into negative 2x cubed. Okay, what would you get if you divide 2x squared into negative 2x cubed? Yeah?
Negative x.
Negative x. And if anyone sees a mistake, let me know, because sometimes I make a mistake. It's hard to keep talking sometimes while you're doing it. It's just easier to go through the problem because you keep stopping and interrupting yourself, but kind of what I have to do to show you how to do it. So we got negative x, let's check it. Negative x times 2x squared is negative 2x cubed. Actually, I think this next one's going to be kind of nice because watch what happens here. Negative x times positive x is negative x squared, and when we subtract, you'll see what happens. Negative x times positive 1 is negative x. I should have brought down the next term. Sometimes I forget to bring it down, but if you forget, it's going to be kind of obvious because when you write your columns, you're going to have a blank spot. So you got to always bring down the next term at some point. Okay, and let's subtract all that. Okay, and if I subtract, Kaylee, what's negative 2x cubed minus negative 2x cubed?
That cancels.
That gone. Let's look at the next one. Madison, what's negative x squared minus negative x squared? 0. That cancels too. So because that happened, we're basically at the last step now. Because when I'm done, I'm going to have an exponent of 1, which is smaller than 2, so we can't divide anymore. 0 minus x is plus x, and then bring down your 2. Your exponent right now is a 1. On the outside, it's a 2, so it's now smaller. You can't keep dividing, you're done. So your quotient is x squared minus x, and your remainder is x minus 2. You could also graph this one and check if you wanted to write it this way. Quotient plus remainder over divisor. 2x squared plus x plus 1. So if you type it in correctly and use parentheses, what we have right here and the original problem should look exactly the same. If they don't, then it could be one of two things. You could have made a mistake with parentheses like I did on the first one. So double check that. Or your answer that you got is just wrong. Okay, one of those two. Okay, any questions on that one? Okay, so far we haven't had any that come out really nice. We haven't gotten any remainder of zeros, which means what's on the outside here is not a factor of what's on the inside. Okay. Hopefully we will get some zeros at some point. Right. This sometimes it seems a little confusing when you see it in words, but if I actually write this out, and I'll use numbers in a second, I think it'll be a little more obvious. So it says that f of x and h of x are two polynomials that you're going to divide. So if you divide them, you're going to get a quotient and you're going to get a remainder. I'm calling the quotient q of x and the remainder r of x. I can't say that the quotient and remainder are going to be numbers. It might not be. In the last problem, they both had letters in them. In the problem before that, I think the remainder was just a number. Okay. So what this is basically showing you is that anytime you divide two things, it's almost giving you a way to check your answer, like another way, without a graphing calculator. Let's pretend that, just to make it simple, let's pretend f of x was 12. You know what, actually, let me do numbers that have a remainder so I can show you that. Let's make f of x 13. Let's let h of x be 3. If I divide 13 by 3, what's my quotient? About right?
Like 4 with a remainder of 1.
Yep. 4 with a remainder of 1. So now let's fill in those numbers in this spot and let's just see what it's saying. 13 equals 3 times the quotient of 4 plus my remainder of 1. Is that true? Is 3 times 4 plus 1 equal to 13? Yeah. So it's basically just saying that whenever you divide two things, you're going to get a quotient and a remainder that always make that formula true. And that's actually how you check your answer when you do basic long division in like elementary school. Take your quotient times, take your quotient times what you divided by and add your remainder. You should get one of the original numbers you started with. If you do, then you did it right. If 3 times 4 plus 1 wasn't 13, then my quotient or remainder is wrong. I did something wrong. Okay. That's all that says. Okay, so remember that the degree of the remainder is always going to be one of two things. It's either going to be 0, which is great when that happens, but hasn't happened yet. Or, worst case scenario, it's at least going to be less than the degree of the divisor. Okay, always. That's how I told you know when to stop, when the degree of the remainder is less than the divisor. Okay. So let's think about this one. The degree of the remainder is always less than what you're dividing by. So what if you divide by something linear? Okay. What's the degree of something that's linear? It's degree, what number? That would be quadratic. So if you divided by a quadratic polynomial, that would be degree 2. If you divide by a linear polynomial, that's degree 1. Okay, that's degree 1. So when you divide by something linear, the degree of the remainder is going to be less than degree 1. Well, the only thing less than degree 1 is degree 0. So what does that mean? If you divide by something linear, you're always going to get a remainder that's degree 0. But what is that? If it's degree 0. Yeah. 1 is an example of what you could get. But in general, that's another example of what you could get. But in general, you're just going to get just a number. Yeah, you're just going to get a number. Anytime you divide by something of degree 1, your remainder is going to be one step simpler than that, degree 0. Something that's degree 0 doesn't have any variables in it, which means it's a constant. It's just a number. Okay, so if you divide by something that's linear, your remainder is just a number. What's linear? X minus 2, x plus 7, y minus 3. Okay? You're dividing by something that's just a letter plus or minus a number. Alright, let's look at this. So let's say I divide two polynomials, okay? F of x and h of x. Now, I'm going to pretend, or specifically, I'm going to pretend that h minus x is a linear polynomial. What is it? I don't know. Maybe it's x minus 5. Maybe it's x minus 10. Maybe it's x minus 7, which would be x plus 7. But it's a letter plus or minus a number. That's all I know. Okay, what's f of x? I have no idea. Just some polynomial. H of x is something linear. So let's look at what that means. If we divide by something linear, and I'm going to apply this idea right here to it. Okay, so if we divide by something linear, the original numerator would equal the denominator, okay, h of x, which I'm saying is x minus c. So there's your denominator, times your quotient. Well, we don't know what the quotient would be, so just call it the quotient. Plus, you would get a remainder. Now, the key here is the remainder. Let's look at this. Is a constant. Okay, it would just be a number. So what I'm really showing you right here is this formula again. But I'm doing it for the specific case where you divide by something linear. So that means your remainder is a constant. Now, the next part would be a little tricky if I didn't tell you where to start, but I'm going to show you something. And what I'm leading up to is a quick way to find the remainder without doing any of the other work. Like if all you want to know is the remainder, we can do that very, very quickly. And this part you probably wouldn't get without me giving you a hint. So this is the hint. Let's pretend that x equals c. Okay, and if you're wondering, well, why? Why would we let x equal c? Just watch what happens if you do. Okay, I'm basically going to take the equation up above, and I'm going to fill in c, which is just the number that was after the minus sign in the division problem. Let's write it out and see what happens. So if we change all the x's to c's in this right here, we get f of c equals c minus c, and that's the important part. Something's going to happen there. C minus c times q of c plus r. Now, with r, it's just a constant. There's nowhere to plug in a variable for r. It's just a number. But look at c minus c. What's c minus c? Yep, 0. So look at what just happened. What's the only thing that's left on that right-hand side now? The remainder. And you have something on the left-hand side. If you take c and plug it into the formula you were given, it will automatically give you the remainder, and everything else just disappears. Right? So here's a formula that says, let's say you took this problem and you divided by x minus 2. If you want me to tell you what the remainder is when I do that whole thing out, I can do it all out using long division, or I can just take the number that's after the minus sign, which is 2, plug it into the original problem in the top, and that's the remainder. So in this problem, if you did it out, the remainder would be 2 cubed plus 8 times 2 plus 5. So without even doing all the long division out, you get 29. So I can tell you the remainder to that problem is 29. Which also tells me something else, because I didn't get a remainder of 0. X minus 2 is not a factor. So I have a quick way I can tell you if something is a factor or not by just checking the remainder. But the key is you have to divide by something that's x minus a number. If I complicate it and make it x squared minus a number, now the whole thing is out the window. You can't use it. You want the remainder there, do the whole problem out the long way. Okay, but this is called the remainder theorem. If you have a polynomial divided by something linear of the form x minus a number, now x plus a number works too. Remember, if you divide by x plus 3, well, I can think of that as x minus a number. Just think of it as x minus that number, x minus negative 3. So technically it could be plus or minus. If you want to find the remainder, take the number after the minus sign and plug it into the formula in the top. And that's your remainder. Okay, so let's try it and see what we get. So this problem says find the remainder. They don't care about the quotient. So find the remainder when you divide f of x by h of x, and then do it again when you divide by g of x. If you were going to do this with long division, and you know what you're doing, I mean, I could probably do that in under 2 minutes. If I use the remainder theorem, I can probably do that in under 30 seconds. Just finding the remainder. So let's do the f of x divided by g of x. So the remainder actually, let's start with h of x. I mean, you could start with g of x. It doesn't matter. We'll start with h of x. Okay. So look at what you're dividing by, h of x. What's the number after the minus sign in h of x? 3. You're going to plug 3 into the original problem, and that's your remainder. And you can check it with long division, where I'm not going to, but you could. So the remainder is 3 cubed minus 3 squared is how much? Nine times 2. Okay. So we're going to use the remainder theorem with the number 3. So we did the first part, 3 cubed is 27, minus, now we have to put 3 in for x here.
36. Negative 36.
So 3 squared is 9, times 2, 18. Plus 3, minus 5. Okay, and once we do that out, that is our remainder. So 27 minus 18 plus 3 minus 5. So that's a remainder of 7. So what does that mean about h of x? If you were to compare that to f of x, we would say that h of x is not a what? Yeah, it's not a factor. So if you were trying to factor f of x, don't use x minus 3. That's not how you would do it. How would you do it? Well, we're not really looking at that today, but we will later on. Okay, so let's do f of x divided by g of x. Okay, let's get the remainder there. So to get the remainder when you divide by g of x, what number would you plug into f of x? Yeah? Negative 1. Because think of dividing by this. You're always plugging in the number after the minus sign. In this case, you're plugging in a negative 1. So negative 1 cubed gives me how much? Yep, negative 1. So, negative 1. Negative 1 squared times 2, so minus 2. And then plugging in negative 1 there is just negative 1 minus 5. Yeah?
Why is it negative 1 instead of 1?
Because this remainder theorem only works if you divide by something that looks like that. It has to be x minus a number. So this one was x minus, there's your number. But this one was x plus. So you want to think of it as x minus, there's your number. So what do we get there? Negative 1 minus 2 gives me negative 3. Negative 3 minus 1 gives me negative 4, which gives me a remainder of negative 9, which means g of x is not a factor. Okay, so if you were trying to factor f of x, neither one of these are the ways you should be doing it. Okay, any questions on that? Yeah.
And so the 2's negative?
It should be, right? Because if you plug in negative 1 here, negative 1 squared gives you positive 1, and then negative 2 times positive 1 is negative 2. Okay, remainder theorem is very handy, especially if I gave you something like and I said to you, what's the remainder there? Well, if you want to set that up with long division, you're going to have to fill in 0x to the 34th, 33rd, 32nd, every single term you're missing from 35 all the way down, So it's going to be really hard to fill all those in. Okay, and with all those zeros, you'd be doing long division like 34 times till you get your exponent all the way down. You're probably going to make a mistake somewhere. If you just take 2 and plug it in here, here, and here, you're good. That's all you have to do. I mean, it might be kind of a big number, but you can do that on the calculator. So that's where it comes in handy. Okay, I'd never ask you to do something like that with long division. That's pretty intense. All right, so let's just go to this. So the factor theorem is basically what I've been telling you all along. I just didn't use that term. But if you have a number right there, such that when you plug it in, it's a root. Okay, that means if you plug that number in, what did we just do earlier? Plugging in the number after the minus sign gave you the what? Gave you the remainder. Well, if you plug in a number after the minus sign, and it happens to give you 0 in the top, that means you just found a root of the top polynomial. And it also means that that number is the remainder. Well, that would mean the remainder just came out to 0. So if the remainder comes out to 0, then you just found something that is a factor. That's basically what the factor theorem says. So you plug that number into the original polynomial, and if it comes out to a root of the original polynomial, then that means you have a remainder of 0, which means this is a factor. X minus whatever the number is. Okay? So it's basically just the remainder theorem, but coming out to 0. It's the factor theorem. All right, so now I'm telling you something is a factor. I want you to show that if you divided this by that, you would get a factor. Okay, you would get a remainder of 0. So rather than doing out all the long division, what's a quick way that I can show x plus 2 is a factor without doing out all the long division? Yep.
Find the remainder if it's 0, then factor.
Yeah, just find the remainder, which means taking the number after the minus sign, plugging it into the top, okay, or plugging it into your numerator, and checking to see if it comes out to 0. All right. So what would be the number that I would plug in to my polynomial? This is what I'm going to plug into. This is where I get the number that I'm going to plug in. Yep.
-2.
-2. So I'm going to do -2 cubed plus 5 times -2 squared plus 5 times -2 minus 2. So I'm checking if -2 is a root in this polynomial. What does that really mean? You're checking to see if you get a remainder of 0. So we get -8. -2 squared gives me 4 plus 5 is 20 minus 10 minus 2. -8 plus 20, what does that give me? -12, yeah, 12. 12 minus 10 gives me 2. 2 minus 2 gives me 0. So what I just showed is that if you plug -2 into that, it's a root. What else does that mean? Well, it means that you get a remainder of 0 if you were to do this long division. And that's it. So that proves x plus 2 is a factor. If I had time, I'd do out the long division and show you, but it would divide nicely. Any question on that? All right. So here's some equivalent statements about roots and zeros. Basically, 3 or 4 things that all mean the same thing, even though they're written a little differently. Let's suppose that you find a number that you think is a root. And I'm going to call that number C. If you think you have a number that's a root, what that means is you plug it into your equation and the answer comes out to 0. That's one way to say it. Another way to say it is if you have a number you think is a root, that's the same thing as saying the number is a 0 of the equation. That's the original way I said it to you. Okay, so if a number is a root, it means it's a 0. It means you can plug it into an equation and get 0 as the answer. It also means it's an x-intercept. I don't know if I write that one down, but if a number is a root, that's where it crosses the x-axis. But that last one, that one's probably the most important. And I did write down x-intercept. This one's important. If you find a number that is a root, that means x minus that number is a factor. All right, so if I told you I'm thinking of an equation in my head, and 2 is a root. Well, if 2 is a root, then x minus my root is a factor. It has to be. All right, so those are all equivalent statements. That second to last one's probably the most important. So what I'm kind of leading up to is I'm going to ask you a question like, I want you to write down a polynomial that would cross the x-axis at 1, 3, and 7. Okay? So what I'm basically doing is I'm giving you 3 roots. Well, if I'm giving you 3 roots, I'm also automatically giving you 3 factors, which would allow you to figure out the polynomial. Okay, so we'll try one of those. Okay, so I want to find a 3rd degree polynomial where the roots are -2, 1, and 3. I could also word that question saying, find a polynomial of degree 3 that crosses the x-axis, -2, 1, and 3. Same question. Bless you. I could say, find a polynomial of degree 3 whose roots are -2, 1, and 3. Same question. All right, so we know that -2, 1, and 3 are my roots. So we're looking for 3 factors. 1 factor for each root. Let's start with -2. Okay, and I'm going to go back to the previous page. So pretend it says -2. -2 is a 0 of the function. It means -2 is a solution to that equation. It means -2 is a root. But what does that mean would be a factor if -2 is a root? Yeah? X plus 2 is a factor. Because remember, if you plug -2 into the equation that we're about to come up with, you have to get 0 as in the equation. That's what this statement says right here. Okay, so I'm trying to come up with an equation that I can plug -2 into and get 0 as the answer, which means getting 0 as a remainder, which means something is a factor. All right? So now I've got an expression right there that if I fill -2 into it, I don't care what the rest of the stuff says. If I plug -2 in, I'm going to get 0 times something, which is 0. Okay, so I have 1 factor all set. How about 1? If 1 is a root, what does that mean would be a factor? Yep.
X minus 1.
Right. You've got to come up with an equation that you can plug 1 in and get 0 as the answer. Well, we're starting an equation. If I plug 1 in, I would get 0 times 3 times something else. Doesn't matter what it is, it's going to be 0. And now I have to have 1 more factor. So if 3 is a root, what would be my last factor? Yep.
X minus 3.
X minus 3. Let's distribute that out and see what we get for an equation. So we get x squared minus x plus 2x minus 2. So that's the first part. We FOILed out x plus 2, x minus 1. Now we'll do it out one more time. Tori, what's x times x squared? X cubed. Yep. Haley, what about x times x?
X squared.
X squared. And Joe? X times negative 2?
Negative 2x.
Yep. And now we'll do the negative 3. Negative 3 times x squared. Joe?
Negative 3x squared.
Negative 3x squared. Okay. Negative 3 times x is negative 3x. Negative 3 times negative 2 plus 6. Okay, let's combine like terms. I'll graph it, and let's see if it actually crosses the x-axis at negative 2, 1, and 3. As long as we did everything right, it definitely should. X cubed. X squared minus 3x squared gives me how much? Yep, negative 2x squared. Negative 2x minus 3x. Yep, negative 5x. And then the last term is plus 6. Now, there's no way I would have ever been able to guess something like that without doing the 3 individual factors and then writing it out. Because when I look at the final answer there, I don't really see the 3 or the 1. I mean, those numbers don't even appear anywhere. That's a coincidence. We got a negative 2, but that doesn't usually happen. Okay, let's graph it and see what it looks like. All right, so get rid of that. All right, so we got x cubed. Let's see, minus 2x squared minus 5x plus 6. And it should cross the x-axis in the 3 spots that we told it to. Let's just put it over here and take a look. So we're looking for negative 2, 1, and 3. Those are supposed to be the roots. Oh, there's your negative 2. There's your 1. There's your 3. It's exactly where we wanted it to cross. All right, so the big thing is if they tell you a number is a factor, or I'm sorry, if they tell you a number is a root, x minus that number is a factor. So if 5 is a root, x minus 5. 12 is a root, x minus 12. Any questions on that one? All right, last one. Okay, let's see if we can factor this one and find the roots ourselves. Now, it's going to work out special because I told you to use factor by grouping. So anytime that you factor by grouping, the numbers have to be set up special. Okay, and they are here. So to use factor by grouping, you write down your terms. So the first 2 have something in common, and the last 2 have something in common. I've already done that here. Anybody see what the first 2 terms have in common that we could factor out of them? Andy?
X squared.
Yep. And if you factor out x squared, you're left with x plus 2. Now the goal here is when I factor out something from the last 2 terms, I'm hoping I get an x plus 2. I've got to see this again later in the problem. That's how factor by grouping works. Okay. What can I factor out of a negative 4x minus 8? That would make that happen. Yep. Yep. Factor out a negative 4. Look what you're left with. X plus 2. Now, look at that. And look at that. What do both of those boxes have in common? Yeah.
X plus 2.
They both have an x plus 2. So now we're going to factor that out. X plus 2. If you factor out x plus 2 from the first box, what's the only thing left in the box? X squared minus. And if you factor out x plus 2 from the second box, what's left there? 4. And now, this first one, you can't really do much with it. But x squared minus 4, you can factor that one step further. How does x squared minus 4 factor? Chris?
X plus 4 and x minus 1, or x minus, wait.
Not quite. It's going to be a pattern because you don't have a middle term here. It's going to be something plus that number, something minus the same number.
Oh, x plus 2, x minus 2.
Yep. X plus 2, x minus 2. So now, this is kind of the reverse of the last problem. I'm telling you the factors. Can somebody tell me what are the roots? Yep.
-2.
The opposite of that number. So -2. Yep. -2 again, and 2. This is what we call a repeated root. Okay. When you have a repeated root, okay, what's going to end up happening is you're going to see a graph, and it's going to go and it's going to touch a number and bounce away from it. So let me type in the original problem so you can kind of see what it looks like. So you've got x cubed plus 2x squared minus 4x minus 8. And the reason it has to just touch the number and then bounce away from it is because if it went right through the number, then it would cross the axis twice. If it went up through it and came back down. So even though it looks like there's only 2 answers here, one here, there's really 3. The trick is that this one is a repeated root. Okay, it's repeated twice. When you write answers on a test, you don't have to write that it's repeated. You can just write that and you get full credit. Okay, but that's what repeated roots look like. They bounce, you just touch it and move away from it. This we've done before, but does anyone remember, or does anybody not remember how to calculate roots on the calculator? Someone remind me, what button do you press to do it? Yep.
Second calc and then you do 2.
Yep, exactly. Second calc, you pick the second option, and then you pick a number left, right, and do a 0, and then the guess. Okay. So that's all the last one was. Usually if I have you find the roots on a calculator, it's because it won't factor by grouping. It won't come out nice. So you need a calculator to do it. Any questions on that? Alright, so all the problems where we divided by something linear today, like x minus a number, that's the ones you can use the remainder theorem for. There's also a much faster way. Anytime you divide by something linear, then long division. Okay, so that's what I'll show you tomorrow. The disadvantage of the way I'm going to show you tomorrow is it only works some of the time. The kind of division I showed you today works all the time. All right, but when the shortcut works, it is nice to use it. It's faster. So that's homework for tonight. It's on 171. So it's 1, 2, 4 through 6. I guess I could have just written 9 through 21 odd. I don't know why I did it that way. But that's what it is. 9 through 21 odd, and then 25, 27, and 32. Sometimes I erase a problem or I change one number. Like maybe I had 16 instead of 15. And that's why I didn't do 9 through 21 odd or something. I must have changed it. All right, so we'll take a look at that tomorrow. Don't forget, I'll be after school Thursday if anybody needs to stop by. If you want to look at your tests now, you got about 10 minutes. Come look at it and ask me questions about it. And other than that, you have 10 minutes to work on them.